Okay, now we're going to the second presentation, and it's also a little going into how can we improve efficiency, how can we actually reduce weight of the electric machine. The topic is a direct cooled electric motor with integral lightweight housing, and the presentator is somebody who's well known to the public of the Motor Summit, as he has given several presentations. It's Martin Doppelbauer from Karlsruhe Institute of Technology. He was the head of electric motor development at SEW, Eurodrive, before he came to Karlsruhe, and actually is holding the professorship for hybrid and electric vehicles. And I know him personally from his activity as a convener of the ICTC2 Working Group 31, where he's looking at efficiency classification of industrial drives. And I know that he's also driving personally an electric car, so I think he's somebody who walks the talk about electric mobility. I'm really looking forward to his presentation here.
Good afternoon and welcome to this presentation. My name is Martin Doppelbauer and I will present the result of a joint research project regarding a new cooling and manufacturing method for housings of electric motors. The presentation was mostly prepared by Andreas Langheck and by Steffen Reuter. The project is a joint effort by the Karlsruhe Institute of Technology, namely the KIT Institute of Electrical Engineering and the KIT Institute of Automotive Systems Engineering, together with the Fraunhofer ICT Institute for Chemical Technology, also here in Karlsruhe. The purpose of the project was the design of a new type of low-voltage electric motor for traction vehicles. We were specifically looking for high power density, high efficiency and low production costs. The aim was achieved by removing the outer cooling sleeve and introducing cooling channels directly into the slots. As we do not have any more to rely on thermal conductivity of the outer housing, we could get rid of the two-part metal housing and use plastic mold instead. This reduces both weight and cost. Furthermore, we were able to integrate the necessary plugs directly into the mold to reduce costs even further. Here we see a section through a conventional cooling sleeve of a permanent magnet synchronous machine wound with round wire. The round wire uses the slot space only partially. The heat is transported from the winding via the insulation paper and the sheet metal package to the cooling medium in the aluminum housing. For the DEmil project, we used flat wire and form-wound windings. This offers a significantly better slot filling. In addition, with the same degree of slot filling, a gap is created in which a cooling channel can be placed. The thermal path leads no longer over the housing, and so there is no need for a thermally conductive material for the housing. At the same time, the thermal path is significantly shortened. Due to the internal cooling, it is therefore possible to use a housing made of poorly heat-conducting plastic, which can also be significantly smaller, as no cooling sleeve is needed. Here is an overview of the results of the electromagnetic design. As we are limited in volume due to the small shot volume of the available injection molding machines, the electrical machine must also have only a small overall volume. The air gap must be a little larger than usual due to the overmolding of the slots. The simulated efficiency over speed and torque is plotted in the left diagram. The desired rated continuous power is marked with a blue line. According to FEM calculation, the motor is capable of 50 kilowatt mechanical output power with an efficiency of up to 95%. The losses at rated operation are shown in the diagram on the right. For all further simulations, it was assumed that the rotor is thermally decoupled from the stator. This assumption has its justification because the air gap is comparatively large and has an insulating effect due to the plastic layer. In addition, the rotor losses are dissipated by a separate rotor cooling. The resulting losses and the efficiency torque specify the requirements for the cooling and the housing. In conventional electric machines, the housing is made of aluminum and fulfills both the stability and the cooling requirements. In the concept that is presented here, we can separate the two properties and have two separate requirements. The polymer that encases the copper and forms the cooling channels is called potting. The housing, shown here in black, holds everything together. The requirements for the housing and the potting are different. In the slot, we need a material with a very low viscosity to fill all cavities completely. Since the material will be between the conductors, it should also be electrically insulating. As the thermal path goes through the material, we need a material with a high thermal conductivity. Our requirements were met best by an epoxy resin filled with ceramics, which is best processed in a transfer molding process. We can also formulate the requirements for the housing. The material should have the required mechanical strength, the material must guarantee thermal stability, and it must be mechanically and thermally stable, that is, we do not want any creeping during the operation. For the housing, we choose a glass fiber reinforced phenol resin, which is best processed in an injection molding machine. I will now show you a short video that will give you an impression of the parts that make up the motor and also of the assembly process of the motor. In this video, we saw that two thermoset materials were used. For the stator, as I said before, a highly filled epoxy resin, which has the main task of heat transport between the coolant and the active materials, so that it should have a highest thermal conductivity. This is processed in the transfer molding process. For the housing, a filled phenolic resin with improved resistance against cooling water, that is, water and glycol. The housing is processed classically by injection molding. Here's a picture of the injection molding machine and the tool for the production of the housing. You can see the side of the ejector with a mounted mold. The phenolic resin offers numerous advantages. Besides the good chemical stability, which is reflected in the improved cooling resistance, the thermal properties are also advantageous. Thus, operating temperatures of more than 200 degrees Celsius are possible and creeping is virtually eliminated. Therefore, it was also possible to dispense with an insert for the bearing. The radial deep groove ball bearings of the rotor are fitted directly into the plastic cover. For the overmolding of the stator, we decided to use transfer molding because we wanted to use material with high thermal conductivity and particularly low viscosity. The material used is so low viscosity that it runs past the screw in a classical injection molding machine and is already partially cured before it reaches the stator. Therefore, the material must be processed in a transfer molding process. The material is not injected through a screw, but through a piston, which can achieve a much better sealing in the cylinder. When the stator is removed from the mold, the overmolded stator is obtained, which has a very smooth and pore-free surface. The surface is directly suitable for sealing with O-rings and ensures a low flow losses due to the low roughness of the walls. The epoxy resin layer can be used directly for centering due to the clever centering of the sheet metal package in the transfer molding tool and the good tolerances that can be maintained. We have created a number of cross-section images to take a closer look at the quality of the transfer molding process. And here are 3 detailed pictures that were taken at different places in the stator. Picture 1 shows a detailed image in the corner of one slot. You can see that the epoxy resin is so low in viscosity that it even fills the area behind the insulation paper. Point 2 is in the middle between the layers. Here too, the low viscosity ensures that the resin is applied without gaps and without air pockets. This ensures a good heat distribution in the slot. Point 3 shows the winding next to the cooling channel. It was noticeable in several cuts that the distance between the conductors and the cooling channel is not always exactly the same, but this is caused by the manual winding technology and would be better if you did it automatically. As we have seen in the video, the overmolded stator and the housing are pushed into each other. This creates the cooling water distribution rings on the B-bearing side of the motor. These are oval in design for optimum utilization of the cross-section. In the right picture, you can see that the separation of the coolant to the outside, that is towards the rotor gap, as well as towards the surroundings, is ensured by O-rings. For reasons of installation space, the sealing between the high pressure and the low pressure distribution ring is only achieved by a gap seal. A certain amount of leakage is therefore unavoidable but also permitted, but leakage at this point only leads to deterioration in cooling efficiency and not to actual leaking of water to the outside or inside of the housing. Since there is no good thermal connection of the bearing to the rotor, due to the plastic housing and because the bearing seat is directly located in the plastic, an additional rotor cooling was integrated. The cooling medium is distributed to the rotor and stator by a common water inlet in the cover. The cooling medium of the rotor is led through a fixed lens. At the end of the lens, the cooling medium ejects and then returns in the hollow rotor shaft. It flows in reverse direction towards the B-bearing shield, where it is sucked off. A 2-stage sealing system is provided to seal the rotor cooling from the rotor gap. The first stage consists of a labyrinth seal. This works reliably at high speeds. When stationary or at low speeds, a V sealing ring seals the rotor gap. At higher speeds, the sealing ring and lips lift off from the mating part due to centrifugal forces, and the sealing ring merely functions as a flinger disc, so it hardly generates any friction losses. A normal rotary shaft seal would be destroyed at high speeds of rotation. The phase connectors are integrated into the housing as well as are the sensor connectors and the thermal sensor connectors and the position sensor connectors. When overmolding the stator, the 3 tongues of the 3 interconnection rings are deliberately not overmolded. These slide into cutouts in the housing during assembly. A pin with crimped-on cable is inserted from above and pre-positioned in the direction of the stator by a wave spring with a union nut. A ramp in the housing presses the pin and tongue together to ensure the necessary contact force for an acceptable contact resistance. The wave spring ensures a sufficient contact force even at changing temperatures or tolerances. In addition, a relative movement of both surfaces occurs during the mating process, thus breaking up any oxide layers. The main advantages of this solution are the reduced number of parts as well as the number of current transitions and the resulting transition losses and lost heat. Multiple seals ensure that no water can enter the plug from the outside or the inside. In order to assess the cooling capacity and the hotspots, the concept was examined in more detail in a thermal simulation. The 2 pictures on the left and the middle show the heat distribution in the motor. You can see that the hot spots are not longer located in the winding head as in any usual machine, but rather now the hot spots move into the yolk of a single tooth. This can be explained by the fact that at this point is the furthest away from the cooling system. In order to be able to estimate the influence of manual winding, the 16 section images were examined and 3 representative sectional images were selected. The evaluation now shows that the worst case is at 212 degrees Celsius, the best case is at 190, and the statistically most likely case is at a temperature of 195 degrees. So all of them are very well within the specifications, and there would even be a temperature margin of 22 degrees. Finally, this picture now shows the comparison of the temperature flow between the winding and the coolant. The DEmil motor is shown in blue. It was examined in comparison to a conventional motor with a water jacket cooling, and that is shown in red. At temperature differences of up to around 60 Kelvin, the heat flow is approximately the same in both systems. It is around 0.1 to 0.3 kelvins per second. However, if the winding temperature is increased further, the heat flow is much faster in the DEmil motor. The best point is reached at a temperature difference of 110 kelvins. Here you get around 1.7 Kelvin per second temperature gradient. And here's a comparison of the achievable continuous power output. Compared to a similar motor with water jacket, the power density was more than doubled, from 2.1 kilowatts per kilogram to 5.5 kilowatts per kilogram. Note also the comparison with the motors of the Tesla Model 3 and the BMW i3. So that was it. Thank you very much for your interest. I hope we will be able to have a short discussion now, or otherwise you can always send me an email to the address that you can see on the screen. Have a good day.
Okay, thank you very much, Martin. And as always, I hope now that I see your face directly here through Zoom connection. Works very well. Hello, Martin. How are you? Thanks for the presentation. I have actually 2 questions from the public. Mr. Schneeweiss is asking actually, how much advantage in weight savings do you see for this kind of new motor concepts? And I was asking myself too, because I'm guessing that the potting itself adds a little bit of weight, whereas reducing the weight of the housing naturally is an advantage. But if you could make an estimation, how much improvement do you see?
The potting actually does not add weight because the plastic housing is lighter than the metallic housing. And regarding the weight, it's a difference if we look at the continuous output power, which is much improved, or the peak power. And the peak power is not improved because the thermal capacity doesn't go up. And regarding the continuous output power, we estimate at least 50% increase in power density, probably twofold. Peak power stays basically the same.
That's interesting. I would have assumed potting itself adds roughly 15% of increase in continuous power. So the direct cooling adds quite a lot more. Huh?
Yeah, direct cooling is really a big step up.
Yeah, very good. The other question is coming from Mr. Marchesi. He's wondering what kind of materials you have used for the lamination of the stack itself. And he was wondering how much did you improve actually the filling factor on the winding as you had, well, you switched to square diameter, but you also had to have some space for the potting itself.
Exactly. Well, the stack material, the soft magnetic material is the same as it was before. I must honestly say I do not exactly know what it was. I think it was a very standard M235 material, nothing special there. And the filling factor, as you said, we can improve it a little bit, but we have to make sure that there are no conductors in the area of the stray flux, or otherwise we have a very high increase in eddy current losses. And so it is a relatively small increase.
Okay, very interesting. So there's one question from my side. It's more about mechanical issues. Basically, if I look now at the slot itself, I have 3 different mechanical materials. I have the lamination, I have the copper, and I have the potting, and well, I have also the cooling channels. So they all have different mechanical expansion properties. depending on thermal increase. So I was wondering, did you experience any problem if you had a sharp increase in temperature rise? You know, if you would go for high power from standstill, low temperature, going to really high power, like you would have going straight on the Autobahn or so?
We have actually not experienced a problem there. There's always a problem in the between the main stator part and the flanges, so that you get no leakage there. The sealing between these parts is critical. But within the slot, because the channel that we create is basically the same material, the same resin that we use anyhow for windings, we did not experience any problems within the slots, no.
Ah, okay, very good. Good, thank you very much, Martin. I think you're also available for further questions if there are. And I wish you a very good remainder of the day. Thanks very much, Martin.
Same to you. Goodbye.